We tackle the problem of finding out where an object is in space, also known as the 6th degree of freedom object pose estimation problem. This entails estimating a position in XYZ coordinates and an orientation in Euler angles. The process for estimating a pose typically goes like this. First, you get a highly detailed mesh of the object by scanning it with specialized equipment. Then you create some training data. The training data is created by aligning the scanned mesh to real photos, or by rendering them using computer graphics. Finally, you train a neural network specialized to each object you want to estimate the pose for. Our goal is to simplify this process by eliminating the need to train a separate neural network for every object. We wanted to make it easier to estimate the pose of new, unseen objects. Our method doesn't require any training for new objects and only relies on a single pre-trained network. To add a new object, you first take some pictures of the object and calculate the relative poses. Our network uses these images to create a latent representation of the object. This only needs to be done once per object. Once you've done the first step, you can use our second stage network to directly predict the pose in a scene. At the core of our method is a pre-trained, frozen network. Given a couple snapshots of an object and a target pose, the network renders the appropriate depth. For pose estimation on a novel scene, we first render the object from an initial view. Pose estimation is performed by computing an error and propagating the gradients back to the pose using gradient optimization. This is our entire process for pose estimation. No training is required. We train our network with 3D models from the ShapeNet dataset. We take random 3D models and render them with randomized appearances in each iteration. We train our network to accurately reconstruct the depth and mask of novel views. During training, we also have an image-based rendering network which reconstructs the color appearance of the object. We only train this network once, and it is a universal network agnostic of the type of object. In order to facilitate a real-life benchmark for unseen object pose estimation, we present the Model-Free Object Pose Estimation Dataset, or MOPED. Our dataset has 11 objects with real reference and test videos. Our dataset is challenging as no 3D models are provided and the videos contain lighting variations as well as noisy masks and depth. Let's visualize what pose estimation looks like using our pipeline. First, we get a coarse estimate of the pose using the cross-entropy method. After initialization, we refine the pose using gradient optimization. Here we compare our method with PoseRBPF, a state-of-the-art supervised pose estimation method. PoseRBPF trains a network for each object using the 3D mesh. Our method, on the other hand, is not trained on these objects and only has access to 8 reference photos. Our method performs on par with, and in some cases even outperforms PoseRBPF. Quantitatively, our method performs on par with state-of-the-art methods on MOPED, as well as other established benchmarks such as LineMod. Thank you for your attention, and please come see our virtual poster at CVPR 2020. We will be releasing our code and data publicly. This work would not have been possible without the NVIDIA GPU Cloud and the NVIDIA Tesla V100 Tensor Core GPU.